Hello, generating functions. Topic of the video is generating functions. What is a generating function? It is defined to be the generating function of a sequence is a power series built with that sequence as its coefficients. So you just literally write down the sequence, but instead of separating it with commas like you might for, just sort of listing out a sequence, right? The sequence itself would just be this list of terms, A0, A1, A2, and so on. Instead, you take those terms and you attach them to increasing powers of x. That's what a generating function is. And so, for example, say you had the constant sequence 1, right? Just 1, 1, 1, 1, 1. Then what would that have as its generating function? Well, that would have 1, right, plus 1x plus 1x squared plus 1x cubed. And if you total that up, that's actually one of probably the most important power series from all of calculus, right? The geometric series. So this is, you can evaluate this by the geometric series formula into a closed form, right? This is, think of a over 1 minus r, right? Where a is the initial term and then r is the common ratio, right? So here a is 1, r is x, and this is the formula. A over 1 minus r, right, becomes 1 over 1 minus x when you plug all that in. So that's an example of a generating function. And sometimes you can find a closed form like this. Sometimes you can't. Sometimes all you can do is write it down and leave it in expanded form, right? But often we want to look for a closed form for a generating function of a sequence. It frequently is extremely useful if you have a closed form for your generating function. So let's look at an example of how to use generating functions. They're often useful for finding explicit formulas for sequences that are defined recursively. And in particular, I want to look at an example of a recursion, right? Here's a recursively defined sequence, a sub 0 equals 0. And then I want the next term, a sub n plus 1, to be 3 times the previous term plus a power of 3. Right, this is going to be the recursion that we want to solve, right? We want an explicit formula. I want something that just looks like a sub n equals, and then I just want some expression involving n and not involving a, right? This would be an explicit formula for this sequence. So I have this recursion. Let's see how this would play out with generating functions. First, I'm just going to calculate a few terms just for fun, right? So if I calculate a few terms, what would I have? Well, a0 by definition is 0. A1 is 0 plus 3, right, is 3. So I'm following the recurrence there with n equal 0 plugged in, right, to get that first term. Now I'm going to plug in n equals 1 to the recurrence to get a2, right? And this will give me 3 times 3 plus 3 squared is 18. Then I'll have a3 is 3 times 18 plus 3 cubed, which would be 54 plus 27 is 81, and so on, right? So there, I'm calculating a few terms, and I'm doing this so that I can write down the generating function, right? So the generating function of this sequence a sub n is what? Well, once again, like we said before, we're going to build a function by taking all of these numbers in the sequence and attaching them to increasing powers of x. 0 is the degree 0 coefficient. 3 is the degree 1 coefficient. 18 is the degree 2 coefficient, and so on. Right, this is our generating function. Now, how can I find the closed form for this? Well, we're going to do it very strategically. Here's what we're going to do. We are going to look at we're going to perform a few algebraic operations here. And in particular, the thing I really want to do is I want to take this equation and I want to multiply both sides by 3x. So I'm going to get 9x squared plus 54x cubed. Right, I'm multiplying each term by 3x. Why would I do this? Well, look at, I'm trying to kind of line it up with the expression just above it, right, is really my goal. So look at, for example, this 81, right? This 81 came from that 54. And what was the 54? It was 3 times the previous term. It was 3 times 18, right? So that's why I kind of want to take this 18, multiply it by 3, but I also want to shift it over 1 degree, right? So that's why I'm saying multiply it by 3x. And then I'm also looking at this 18 and I'm saying, where did that come from? Well, it came from, part of where it came from was 3 times 3, and 3 was that previous term. So, if I take this and multiply it by 3x, that's going to get that 9 under the 18 on terms of common degree, right? The 54 under the 81. So I'm seeing how the recursion of the sequence, how I can kind of line that up with what's happening algebraically. Now I can also look at these other parts, again, very intentionally, very strategically. What else do I need here? I need a 3 squared, a 3 cubed. So let me just write those down, but I'm going to write them down now as terms in a power series rather than just terms in a sequence. So what do I need? I need a, this is there was a 3 on this index. There was a 3 squared on this index, right? There was a 3 cubed on this index, and so on, right? Now this is actually something that we know a closed form for, what I just wrote down here, because look at what this is. This is a geometric series, right? We can apply the geometric series formula. This is a geometric series with initial term 3x and common ratio actually also equal to 3x, right? 3x is the first term in this series, but it's also the common ratio, right? It's what I multiply by to get from term to term is 3x, right? 3x times 3x is 9x squared. 9x squared times 3x is 27x cubed, and so on. So evaluate this, a over 1 minus r, right? So do a over 1 minus r, we get 3x over 1 minus 3x. There's our expression for that infinite series, right? So now, if you look at this, I have 3 equations, and they are related in that if you add the second and third equations together, right? Look at equation 2 and equation 3. If you add those together, you're going to get equation 1. We built them that way, right? Very, very intentionally, by looking at how these terms were being generated in the recursion, in the sequence, right? And then doing algebra to make our generating functions reflect that recursion and how those coefficients were built in the first place. So, right, you look term by term, you say, okay, look at this, equation 2 plus equation 3 actually produces equation 1. So let's write that out. What does that look like algebraically? It looks like 3x fx plus 3x over 1 minus 3x equals f of x, right? Well, now there aren't any infinite series anymore. Now it's just finite expressions, right? Solve it for f, and we'll get a closed form for our generating function. So let's subtract, right? We're going to solve for f. So I'm going to subtract the this f of x term to get f of x minus 3x f of x. And then I'm going to factor out this f of x. And then I'm going to divide both sides by 1 minus 3x, right? So what do I end up with? I end up with a closed form for the generating function for our sequence, right? It's going to be this, 3x over 1 minus 3x squared. So now what can I do? Well, now forget that this function came about as a generating function from, representing some recursively defined sequence. And instead, now just go back to Calc 2 and just ask yourself, what is the power series? What is its power series, right? Find a power series for this function, right? Imagine it like a calculus exercise. So what can we do there? Well, I can say the easiest way to get this is say, okay, this is 3x. I'm just gonna that kind of put that out on the side there. And I'm gonna actually just the x I'm gonna put out on the side there. I'm gonna leave the 3, and I'm gonna look at this expression and say, you know what, this expression is a little bit ugly. And I want to think of it in a cleaner way. I want to think of it as the derivative of a nicer function, right? This is a trick from Calc 2. Sometimes a given function maybe is sort of difficult to say what the power series is, but maybe its derivative or antiderivative has a nicer representation, right? So this is this function, this 3 over 1 minus 3x squared. That is the derivative of 1 over 1 minus 3x, right? Think of the denominator as a -1 exponent. Do the power rule. So the -1 power becomes a -2 power, right? And then there's also a chain rule that spits out this this -3, right? But fortunately, the negative on the -3 from chain rule will cancel with the -1 from power rule. So those go away, and sure enough, the claim is correct, right? So this is the derivative of a geometric series. Well, now what I can do is I can use the geometric series formula, right? I could say this is the sum of all powers of 3x, right? It's just the standard 1 over 1 minus x geometric series with 3x substituted into it, right? At which point I can say that I can actually expand this power, right? 3 to the n, x to the n, and then I can take a derivative, and it's a derivative with respect to x, right? So the 3 and the n's, you just treat those as constants. Well, 3 always treated as a constant. Treat n also as a constant, and treat x as the variable, right? So do the power rule on x to the n. Okay. Now multiply this x back inside. So it's going to bump this x to the n minus 1 back up to x to the n. Look at what we have. This summation, right? This summation has some formula, n times 3 to the n times x to the n. This is the coefficient. Well, this must be, this formula, this must be a sub n, right? Because what was this? This was a representation, power series representation of f. But what was f? F was defined to be the generating function for a sub n. See, f, what does f have as its coefficients? F has the sequence a sub n. And we just found a formula for the coefficients of f, right? Namely, in 3 to the n, right? So we now have an explicit formula for a, right? A sub n is actually n times 3 to the n, right? Let's check a few terms. So if I do a0, sure enough, I get 0, right? 0 times 3 to the 0 is 0. If I do a1, I get 1 times 3 to the 1 is 3. a2, I get 2 times 3 squared is 2 times 9 is 18. And if I do a3, I get 3 times 3 cubed is 3 times 27 is 81, right? So sure enough, our explicit formula confirms the terms that we were generating with this recursion, right? And so we did it. Here is our explicit formula, right? So just to recap a little bit, what happened here? Well, we had this sequence, right? This recursively defined sequence. We calculated a few terms, and maybe a pattern doesn't just jump out and say, here I am, right? When you're calculating these terms, right? But you can still find a formula for the sequence, at least in this case, and in lots of cases, using a generating function. What do? Take those terms from your sequence and build a power series out of it, right? Use some algebra on power series to reconstruct that recursion, right? Here I was saying, looking at it, say that 81, where did it come from? Well, it was that 81 was a 27 plus a 54, right? And figure out how to build power series to get that to be those corresponding terms in the degree 3 term and in all the terms, right? So once you have that algebra, you'll get some relationship that will let you, some equation, right, that will let you solve for a closed form for your generating function, right? In this case, it was a rational function. And this rational function is the denominator was degree 2. It had a repeated linear factor. So the easiest way to get a power series for it was to differentiate a geometric series, which you can just do term by term, right? So you differentiate that term by term, good old power rule. And there we go. Whatever that coefficient is, that's your formula for a sub n. So we were able to go from a recursive formula to an explicit formula using a generating function. Great. Thanks so much.